to think about how, the fact that if the k value, so the y-intercept is too large, then I only get one intersect, and how that's related to this specific point here, okay? So let's go ahead and do this. And just to say, whenever you see this language of two distinct points and you have quadratics going on, you should be thinking about discriminants. So I've just rewritten the equations of the two curves and made them equal to 2y to get rid of the factors of a half. So again, it's basically like solving simultaneous equations. Well, it's exactly that, right? Which is, solving where two curves intersect one another, but then obviously we're going to use a discriminant to sort of place a bound on k for which the curves have sort of two real and distinct intersection points. So this gives me the following. That gives me minus x plus 2k, just solving the simultaneous equations, is equal to x squared minus 2x plus 11. So rearranging this gives me x squared, and then I have minus x plus 11 plus 2k is equal to 0. And if I want to sort of work out the condition on k such that this quadratic has, two distinct solutions, I use a discriminant, so b squared minus 4ac. So b is just minus 1, so that squared is 1. So 1 minus 4, well, a is 1, and then c is 11 plus 2k. And of course, to have two distinct solutions, this needs to be greater than 0. And if you solve this inequality, you get 43 over 8, k is greater than 43 over 8. I wrote that slightly weird. But yeah, so that's what we get for the upper bound, right? And that sort of corresponds to, the lower bound. And that corresponds to k, that, saying that basically this k has to be above this point here, okay? And then we need to think about the other bound that's going to sort of, stop, this line having two distinct intersection points. And that's basically related to the fact that, well, at this point here, this is kind of the last point, right? So if the line, with this equation here, goes through this point here, so basically just touches at this point here and goes through here, that's kind of like the last point, right? The limiting case. If the k value, which is this y value here, is any higher, then then I no longer have two distinct intersection points. Okay, so how do I figure out what that k value is? Well, I just use the fact that I can work out the coordinates of this point using the fact that I know the domain sort of starts when t is equal to minus pi over 4, which means that this is the point where t is equal to minus pi over 4. So I can work out the coordinates of this point, and that will fix the value of k when I substitute that into the general form of this straight line. So let's go ahead and do that. And so if you go ahead, and I encourage you to do this, and substitute in t is equal to minus pi over 4, right, which we know corresponds to sort of this point here, you get the following for the Cartesian component, so it's minus 1, 7. And the idea is that, okay, we can find out what the k value is, what the y-intercept of that straight line is, if it passes through the points minus 1, 7, because we know it has a gradient of minus half. So, just dividing this by 2 again to get back to the original equation. What do we have? So subbing in this point, we have 7 is equal to, we have minus a half, lots of minus 1,